All right, welcome back. We are jumping into section 8.1, so we are getting into chapter 8 here. Chapter 8 is going to have to do with a lot of right triangles. 8.1 should be pretty easy because we've actually been using this theorem for quite some time. We're just going to go a little bit more in depth into it. So today's lesson is called the Pythagorean Theorem. So there's no secret here. I know you guys have been working with the Pythagorean theorem for quite some time, and we've been embedding the Pythagorean theorem into several problems into our geometry studies. So let's just jump into this. It says Theorem 8.1, the Pythagorean theorem. If a triangle is right, so that's super important. Make sure you know that this only works for right triangles. If a triangle is right, then the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. What does that basically say? It says a squared plus b squared equals c squared when c is the hypotenuse and a and b are not the hypotenuse. They are just the legs. So one thing that used to always trip me up was it took me quite some time to realize that this only worked for a right triangle. I saw like an obtuse triangle and I thought the Pythagorean theorem worked on this, but it only works on right triangles. Now, luckily, right triangles are all over the place in the study of geometry and in the real world. So you'll be able to use the Pythagorean theorem quite a bit. Now, if we look at this, if we wanted to look at a geometric proof, I'm actually going to scribble out the coordinate proof. I was a silly willy. I used to teach this and I'd go over and show a coordinate proof. And I would show that if we called this a length of A and this a length of B, and then I went over and did the distance formula between these 2 points, then we would be able to get A squared plus B squared equals C squared. I was being a dummy though, because I wasn't even thinking about the fact that the distance formula was developed from knowing that the Pythagorean theorem was true. So you cannot go over and use a formula that is pretty much the formula that you are trying to prove is true. So I'm not going to be doing a coordinate proof. What I am going to be doing is showing a geometric proof, but I'm going to do it in two different ways. First off, I'm just going to show you why this is true. Let's say we are looking at a 3, 4, 5 triangle. One, two, two, two. If we went over and made a square that was coming off of this side right here, it would be in this case, with the exact example I'm giving here, would be a 3 by 3, which would be an area of 9. If we went over and looked at a square coming off of this side, which is a length of 4, so it'd be a 4 by 4, that would be 16. And then this one would be 5, a 5 by 5, which is 25. And what you find is that the area of this plus the area of that equals the area of this one. Now, instead of calling that 3, 4, and 5, it's basically if this was a length of A, a length of B, and a length of C, this would have an area of A by A, which is A squared. This would be B by B, which would be B squared. And this is C by C, which is C squared. The area of this one plus the area of that one will equal the area of that one. Now, the reason why this isn't actually a proof and more of just an example is because we know when we're dealing with proofs in math, we should really not be using like specific numbers because that's a specific example and that shows it works in this case, but it doesn't show it works in all cases. So what I'm going to do is I'm going to do a slightly more complex example here. So let's say we went over and had our right triangle here. Call that A and call that B and call that C. Now what I'm going to do is I'm going to make another right triangle coming off of this one. That. Unfortunately, I did not make them perfectly the same, but this could be A and that would be B. Now I'm going to make another triangle coming off of this. So let me try a little bit better. This is a length of A, that's a length of B. And if I did one more, this would be a length of A, and this would be a length of B. All of these would be C's inside, and we would end up with a square. Okay, I'm going to show you how this theorem works. So or how this proof works. So I'm going to go over and talk about the area of this whole entire thing right here. And the way I'm going to do that is I'm going to look at the whole entire square. The square is this is going to be a length of A plus B, and this is a length of A plus B. If I went over and found the area of this whole entire thing, it would be A plus B squared. That is a way of talking about the area of that. And if we actually multiplied that out, A plus B times A plus B, when you FOIL it, you get A squared plus AB plus another AB plus B squared. So A squared plus 2AB plus B squared. That is one way to talk about the area of this whole thing, and that would be by just looking at the side length, this whole entire side length here, and this whole entire side length, and multiplying those together. Now, a different way of doing this is I'm going to add up all the parts. We have 1, 2, 3, 4. We have 4 triangles, and each one has an area of 1/2 its base, which I'm going to call A, times its height, which I'm going to call B. So that would give me 2AB. So that's accounting for that part, that part, that part, and that part. Now we also have to account for in here. This is a C by C, which is just C squared. So what you should understand is that this is one way to calculate the area of that big figure, getting this, and this is another way number 2, to find the area of the same exact figure. Now, if they both are the actual area, we should be able to set them equal to one another. So let's go ahead and do that. The area, A squared plus 2AB plus B squared, should equal the area no matter how we went over and calculated it. This is the other way we calculated it, 2AB plus C squared. And what we can do here, you're probably wondering, what does this have to do with the Pythagorean theorem? Now watch. I'm going to do the subtraction property of equality. So I'm going to do subtracting by 2AB on both sides. And what do we end up with? A squared plus B squared equals C squared. So there's many, many, many different ways to prove the Pythagorean theorem. And this is the one that I wanted to do because it uses our algebra skills. Lovely. All right, the reason why I was able to spend so much time doing that is because you guys should already know how to use the Pythagorean theorem. So this part should be really easy. Most important thing is remembering that C is going to be your longest side, which is always across from your right angle, and it's called your hypotenuse. So this one right here is we're going to use A squared plus B squared equals C squared. 24 squared plus 7 squared equals C squared. You could have also called it x squared. I just called it c squared. You then take out your trusty calculator. You say 24 squared gives me 576 plus 49 equals c squared. When I add those together, I get 625 equals c squared. And then you square root. And the square root of 625 is 25. And that's the missing side. Okay. I'm going to skip this one because it's basically a repeat of the same exact thing. Now look at this one. A squared plus B squared equals C squared. We can use this because we have a right triangle. Now what are we missing? A, B, or C? Well, this you can call your A side or your B side, but just don't call it your C side because your C side is your longest side over here. So I'm going to call it my A side. So A, we don't know, which is going to be x squared plus 8 squared equals c squared, which is 20 squared. X squared plus 64 equals 400. Minus 64 minus 64, and that gives you x squared equals 400 minus 64. 400 minus 64, that gives me 336. And when you square root 336, second square rooting 336, and that gives me approximately 18.3. You also could have gone over and simplified that. Remember where you go over and you say 336 and you divide by 2 until 2 doesn't work. We'll talk about that a little bit more in class, just to remind you guys how to simplify your radicals. So now let's keep on moving on. Let's say this is supposed to be a real world one. We have a length here of 6, a length here of 5, and we don't know what that is. Okay, let's find out what that is. So once again, 6, 5, we don't know. I want you guys to try this one, find out what x is going to be, and round to the nearest tenth. All right, you should have gotten 5 squared plus x squared equals 6 squared. 25 plus x squared equals 36. X squared equals 36 minus 25. 36 minus 25 is 11. Square root, second square root of 11, and that gives me around 3.3. Should have gotten right 11 or 3.3. All right, let's keep on moving on. Now, of course, we can go over and introduce more difficult problems such as this one. This one you're going to have to solve using solving by factoring or the quad formula. So let's go ahead and work through this problem. We know that we can use the Pythagorean theorem because it's the right triangle. So I'm going to do the a side squared plus the b side squared equals my c side squared. At this point, whenever you go over and you're squaring a binomial, you're not allowed to distribute the squared in. What you're going to do is do some side work. X plus 2 times x plus 2. And that's going to give me, by FOILing, x squared plus 2x plus 2x plus 4. X squared plus 4x plus 4. So you have x squared plus 9 equals, ooh, look at this. This is kind of nice, actually. 4x plus 4. Why am I saying this is nice? Watch what happens. When I subtract x squared from that side, it goes away completely on that side, and we no longer have a quadratic. So you have 9 equals 4x plus 4. And now we can go over and solve this. Minus 4, that's 5 equals 4x. Divide by 4, divide by 4. You get 5/4. Check to make sure that it actually works and it makes sense for a problem. Is it possible for those side lengths to be 5/4 and then 2 plus 5/4? It is. Okay. There you go. Now let's go ahead and look at this one right here. If we did the Pythagorean theorem, which we're allowed to do because it's a right triangle, you'd have x squared plus x plus 2 squared equals x plus 3 squared. So this left side is going to be x squared. We just did this, so I'm not going to, it's right here. We just did it. So plus x squared plus 4x plus 4. Now I do have to go over and FOIL that. X plus 3 times x plus 3. It's going to give me x squared plus 3x plus 3x plus 9. X squared plus 6x plus 9. X squared plus 6x plus 9. Now, when I go over and I subtract x squared from this side and I subtract x squared from that side, we still have an x squared. X squared plus 4x plus 4 equals 6x plus 9. Now, at this point, what we need to do is we need to get, since we know we're going to have a quadratic, we have to get one side equals 0, minus 6x minus 6x, minus 9 minus 9. So you would end up with x squared minus 2x plus 2 equals 0. At this point, let's solve by factoring. Hopefully we can actually factor. If not, we're going to have to do the quad formula. A times c is 2. B is negative 2. Two numbers that multiply to get that and add to get this. 2 times 1, no. Negative 2 times negative 1, no. Ugh. Okay, so since we now know, I can't think of, there is no winning pair, that means that you cannot solve this by factoring. You're going to have to solve by quad formula. So I'm going to show you how to do that. A is going to equal 1, B is going to equal negative 2, and C is going to equal 2. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. 2 plus or minus the square root of 4 minus 8. Let's make sure I'm doing everything correct here. Oh, I'm a dummy. How am I a dummy? Because that was not actually the number. This was 4 minus 9. 4 minus 9 gives me negative 5. Oops. So this is actually supposed to be, let's see if we can solve by factoring. Negative 5 and negative 2. Negative 5 and 1, or 5 and negative 1. Darn it, nope, still can't solve by factoring. So A equals 1, B equals negative 2, C equals negative 5. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. 2 plus or minus the square root of 4, that gives me positive 20 over 2. 2 plus or minus the square root of 24 over 2. And if we were to round this, you would basically go over and say 2 plus rad 24 divided by 2. Find out what that is. Let me go ahead and do that. 2 plus rad 2 plus square root of 24 divided by 2. And that gives me approximately 3.4. And if we did 2 minus the square root of 24, and then we divided by 2, we'd end up with negative 1.4. Now, which one of those does not make sense for our problem? That one does not make sense for our problem. So this would be your only solution. Ugh, that one was ugly. All right, now you should have known how to use the Pythagorean theorem. Now what we're doing here is we are going to talk about something called the Pythagorean triples. All that means is 3 numbers that satisfy the Pythagorean theorem, and they're all integers. So I'm just going to give you a few of them. The number 3, 4, and 5 are going to be a Pythagorean triple, and any multiples. So you can multiply all those by 2, getting 6, 8, and 10. Cool. Multiply by 3, 9, 12, and 15. Why is that useful? Well, mathematicians are lazy and efficient. If you remembered the Pythagorean triple, 3, 4, 5, and you see 3 and 4, and those are the legs, then you know this one's going to be 5. You can skip the whole Pythagorean theorem. The only other one that I'd really like you to know is 5, 12, 13, and any multiple of it. So 10, 24, and 26. If you don't remember it, you just do the Pythagorean theorem. But this will save you some time. So those are your Pythagorean triples. There's many other ones. These are the only ones I expect you to know. 3, 4, 5, 5, 12, 13, and any multiples of those. Okay. So let me show you an example really quickly. This is a 3, 4, 5, 1. It's just that multiplied by 3. 3 times 3 gives me my 9. 4 times 3 gives me my 12. So without doing the Pythagorean theorem, I already know that's going to be 15. Now, one really important note is that this is not a Pythagorean triple. If you have a 3 here and the 4 is hypotenuse, that one's not going to be 5. All right, now one last thing I got to show you, that is this. This is going to be the converse of the Pythagorean theorem, okay? So the converse means you're flipping the theorem, the conditional statement. So we knew that we had if the triangle was right, then a squared plus b squared equals c squared. Now, one important thing for you guys to know is that the opposite, not the opposite, but the converse of this is going to be true. So you can switch those. If a squared plus b squared equals c squared, then the triangle is going to be right. Right? So if I gave you this triangle, 3, 4, and 5, and I said, hey, is this a, let me take away this. And I said, is this a right triangle? If you can show that that squared plus that squared equals this squared, then that has to be right. We're going to go one more step though. We want to know more than that. We want to know how to figure out if it's obtuse or acute as well. So let's just start by filling these out. If a squared plus b squared does equal c squared, then the triangle is going to be right. Now I want you to think about this. What would happen if the c side got smaller? So instead of a squared plus b squared equaling c squared, if a squared plus b squared was bigger than c squared, the c squared part got smaller, therefore that left-hand side is bigger. Imagine a right triangle. This is where a squared plus b squared equals c squared. Now imagine that the c squared part got smaller. Would it become obtuse or acute? Acute. And then imagine this, instead of a squared plus b squared equaling c squared, a squared plus b squared, instead of it equaling c squared, imagine if the c squared part got bigger, aka c got bigger, then what does that do? Does that make it obtuse or acute? Makes it obtuse. So if a squared plus b squared, if the c squared part is bigger, that means c got bigger and it must be becoming obtuse. So that's how you figure out if it's equal, then the triangle's right. If the c squared part got smaller, then c got smaller, therefore it's acute. And if the c squared part got bigger, then c got bigger and it must be obtuse. So let's go ahead and just do a few of these really quickly. So let's say you had this. I'm going to scribble, I don't want it to get super confusing. Let's say 6, 9, and the third. No, let's do 11. Okay, so let's see what is true. We have 6 squared and 9 squared, and we're going to see how it compares to 11 squared. 36 plus 81, we're going to see how that compares to 121. I'd put 36 plus 81, 117, and 121. What side, or let's just ask what happened to the c squared part? It looks like the c squared part got bigger. It's not equal to, it's the bigger one. So when c gets bigger, what happens? Becomes obtuse. Okay. Now let's try another one. Let's do 6, 8, and 9. Let's see what we get here. So we're trying to see how does the 6 squared plus the 8 squared part compare to the 9 squared part? How does the a squared and the b squared part compare to the c squared? 36 plus 64 and 81. Gives me 181. What happened to the c squared part? The c squared part is smaller, which means c got smaller. Imagine a right triangle, but that would be if a squared plus b squared equals c squared. Now imagine the c squared getting smaller, aka c getting smaller. What happens to this? Does it become obtuse or acute? Acute. All right. Let's do one more. Let's say that we had, I'm going to give you an easier one. Let's say you had 10, 24, 26. Those are your a and b because they're not the longest side. So let's see how 10 squared plus 24 squared compares to 26 squared. It's 100 plus 24 squared. 24 times 24 gives me 576. Oops, 576. Let's see how that compares to 26 times 26, 676. This gives me 676, and that's 676. They're equal. What happens when the a squared plus b squared part equals the c squared part? It is going to be right. Right? All right, we're going to talk about more of this in class, but we are running low on time. So I want to show you one little application here. So when would you actually use this? Construction workers use this all the time. Let's say you were doing a project at school and you wanted to put in a tetherball thingy in the 6th grade playground area. And you wanted to make sure this thing was standing perfectly up at 90 degrees. Well, one thing you can do, and this is what some construction workers do, they will measure up 3 feet. They'll measure over 4 feet, and then they'll measure this. And they know that if they get 5 right there, then it is standing up at a 90-degree angle, because they know the converse of the Pythagorean theorem says if a squared plus b squared equals c squared, then it is a right triangle. So that is one way you can do it. If you're ever trying to make a right angle, you can measure 3 feet along one side, measure 4 feet along the other side, and then make sure that this is 5 feet. If it is 5 feet, or 5 units, whatever unit you want to use, you will know that this is definitely going to be at a right angle. All right, so one last thing, a little reminder. If you have a right triangle, then a squared plus b squared equals c squared. It only works for right triangles. Do not forget that c must be your hypotenuse. Okay, then we learned if a squared plus b squared equals c squared, then it is going to be a right triangle. That's called the converse of the Pythagorean theorem. We also looked at if you had a squared plus b squared and the c squared part got smaller, meaning the other side was bigger. Imagine a right triangle where c is getting smaller, it's acute. Don't try to memorize this. And then if you had a squared plus b squared and you had c squared, but the c squared part got bigger, that means c got bigger. Imagine a right triangle and then get the c side, make it bigger. That'd make it obtuse. Thanks for watching. Sorry that one ran so long.